Okay, so continue see our result. So this one, we already have 10,000 simulation. So then we use the TVD to find the TVD and represent for our statistic. So here, I didn't explain earlier is we have the bin. The bins actually use the data between 0 to 0.005. 0 to 0.05. But before this one, I want to show you if we don't use this one yet. Okay. So if we don't use any bin yet, okay, so that's why here, because if we don't use any bin yet, so that's why we see the range is between 0 to 0.05. But since they are not evenly for the interval, so that's the reason we add the bins is between 0 to 0.05. So then we have each interval is 0.005. So that's the reason we add the bin like this. So if you see like that, since we already know the range, so sometimes you don't know what kind of range you want to use. So you just give them the default without bins. So once you know the range, then we can adjust the interval in between. So if so, you can see very clearly. So the biggest one, they are happen between 0.015 to 0.02. Okay, so then, but they are mostly between 0.01 to 0.0. This one is the most, yeah. So between 0.01 to 0.025. Okay, so that's our simulation result. But the most important thing, we want to check our alternative point of view, right? Okay, so that's why back to see here. Let me add this one again. Okay, so we have our observed data. Okay, so this one is our observed TVD. So according to the panel's result compared to the eligible ratio, then we find out our observed TVD is 0.14. So where is 0.14? Actually here not even 0.1 yet. So 0.1 actually is quite here, far away from here. So that's why we can see in our distribution, our simulation, we failed to make the random selection. But actually the result actually very far from that. So that's why from here we can know in our the sample data we get, they are not really meet the random selection. So our jury selection actually is not random enough. So of course that will include many different reasons. Okay, so you can think about that. So here we have 0.14, far away from our distribution. What does that mean? Discuss with your classmates, of course, pause the video. So what does that mean? Actually, we should have like our early example. We should have our two viewpoints. So just we didn't list here yet. So that's why you can try to write down your two viewpoints. So remember earlier our example, we only try to have the alternative viewpoint is see if they are biased against the black man. So then from this new example, we have 5 different categories. So our model viewpoint is still the same. The people on the jury panel were selected at random from eligible population. So if we want to add, we can say actually we don't have to add, because if they are really random select, so no matter how many categories, they should select randomly. But this, our alternative viewpoint, we can say is, no, they were biased. Against which one? Actually, this one, we still not specific to say that. But one thing is, that's why we say they are really far from our simulation. So they may have the reason, maybe they don't have enough Latino juror, or they have too many Asian juror or something, but they are all against our model. So depends on your your alternative viewpoint. you can list the different things to see how we do the our hypothesis testing. So that's why here the first thing before we talk about the summarize the hypothesis testing again, I want to give you the summary of the method we just did. So to assess whether a sample was drawn randomly from an unknown categorical distribution. Okay, so if we have more than 2 categories, so we use the TVD, the total variation distance, as the statistics, because it measures the distance between categorical distribution. Here the categorical distribution you can see is more than 2 categories. So sample at random from the population and compute the TVD from random sample. We repeat numerous times. So from our example, we do 10,000 times. So after we're done, after the simulation, we create our empirical distribution of the simulated TVDs. So then we compare the distribution with the actual TVD to see how they look like. So if they far from 1, so that we know they are biased. But if not, of course, if they are within the accepted range, so then we can accept the model. So now we see about 3 examples. Of course, we will do more in the next lecture. But the 3 examples you see, actually we are doing the testing hypothesis. So what is hypothesis testing? So that's the test chooses between 2 views of how data were generated. So the views are called hypotheses. So basically, right, you have 2 viewpoints, 2 hypotheses. So the test pick the hypothesis that is better supported by the observed data. So on the other hand, right, you have 1 point of view and 2 point of view. Basically, they're against each other. Okay, so then according to your testing result, so then we can know from your simulation result compare with the observed data. So we want to know which hypothesis we should be accept or which one we should be rejected. So these 2 viewpoints, earlier we said that's the model and alternative. But here in the statistic, we call they are null and alternative viewpoint. The method only works if we can simulate data under one of the hypotheses. So one thing is, like earlier we say, the null hypothesis and alternative hypothesis is against each other. So on the other hand, you only need to simulate the data under one of the hypotheses. But mostly, right, like we say, they are checked to see if they will accept alternative hypothesis. So your null hypothesis is a well-defined chance model. So again, that's the model we define. Your model has a well-defined assumption. So this well-defined chance model about how the data will generate, we can simulate the data according to the assumptions of the model. Then we can simulate data under the null hypothesis. So after we simulate that, right, so we compare to our observed data, then we know should we accept the null hypothesis or reject. And the alternative hypothesis actually is a different, you can say opposite or a different point, a different view about the original of the data. On the other hand, it's a different view from the null hypothesis. Is that okay? So think about that before you move forward. So after we understand the null and alternative hypothesis, according to how they define that two views, we need to do the simulation. The most important thing before your simulation, you need to know how you simulate it for. So that's why you need to have one statistic chosen. So this statistic chosen statistic we call the test statistic. So this statistic that we choose to simulate to decide between these two views or these two hypotheses. It's important to choose the statistics. So that's why you need to ask those questions. What values of the statistic will make us lean toward the new hypothesis? And what value will make us lean toward the alternative? Preferably, the answer should be either just high or just low. You try to avoid both high and low. So if you really have high and low situation, so the way to solve that, we just choose the absolute value. So that's why your absolute value, then we would make us just preferably the answer should be just check if they are too high. So after you choose the test statistic, so then when we do our simulation, or we can say that's prediction because it's under simulation. So the prediction under the null hypothesis, we simulate the test statistic under the null hypothesis. You simulate among a big number of a time. Then you draw the histogram of the simulated value. This will display the empirical distribution. Right, so we remember empirical distribution actually just you run so many times, then you have your result. So this empirical distribution of the statistics is under the null hypothesis. If this prediction about the statistic make the null hypothesis, it shows all the likely value of the statistic. Also, how likely they are. Okay, so we see because we are simulate so many times. So your result actually represent the null hypothesis with all the likely value you display. And how the distribution look like. But the most important thing you need to understand, the empirical distribution is came from big amount of simulation. Even they really very approximately look like the probability distribution, but they are not. They just because the big amount of repeated time make them look like, but they are not exact probability distribution. So that's one thing you need to pay attention. The reason is, no matter how many times we run, it's impossible we can generate all the possible random sample. We just try to run as many as time to cover as much as we can. So here is the conclusion about the hypothesis testing. But the content, you basically already see them so many times. So when we have the choice between the null and alternative hypothesis, we compare the observed test statistic, so observed data, with the simulation generate the empirical distribution according to the null hypothesis, according to our model. If the observed data is not consistent with the distribution, then the test will favor the alternative because the model doesn't reflect the consistent reflection with the observed data. The data is not consistent with the model, but the data is consistent with the alternative. So how we decide the value is consistent with the distribution or not? That's why we make the histogram. So the visualization is important. From the visualization, we can see the observed data with the histogram on the empirical distribution. If the observed data is far from the distribution, of course, we know they are not consistent. But then I know you guys will ask, how far mean not consistent? So that's why we will show you more about the confidence level in the future lecture. So that's our comparing distribution.